Oftentimes, it's good game design to allow players a strong single-player experience to play against or engage with non-playing characters, especially in cases where your world's concurrent player counts are not enough yet to ensure consistent matchmaking amongst players. This is usually where AI, or artificial intelligence, comes into play. This term may sound intimidating or scary to implement, but not to worry. Today, our goal will be to demystify AI so that you have the beginnings necessary to build out your own AI systems. MapleStory World's AI Behavior API operates based on a behavior tree system, a system that essentially allows our AI agents to make decisions based on its behavior tree and how it's constructed. So why behavior trees? Before we can answer that question, let's take a step back and explain what motivated our decision to build our tools around this behavior tree system. Let's first begin with some different alternatives and trace our path to behavior trees, starting with FSMs. FSMs, or finite state machines, are relatively easier to configure and more intuitive to design. It's primarily used in designing AIs and are comprised of state and transition. If certain conditions are met while performing an action for a state, it transitions to the next state. For example, if a player approaches a monster currently in the waiting status, the monster changes to attacking status to perform actions and attack the player. However, as the FSM model increases in scale and complexity, it becomes increasingly difficult to see and reuse the flow of states. So, hierarchical finite state machines, or HSFM, were introduced to modularize these states into groups so that groups of states can be better organized and reused. However, it's difficult to reuse the individual states. Each subordinate state has to be transitioned from a certain group of states, making it impossible to access an individual state from another group. For example, if a state named hit is a substate of the idle or battle groups, you have to add the hit state under the idle and battle state respectively. So behavior trees then offer a nice blend of organizational capability as well as reusability. Unlike finite state machines, which consist of state and transition, each node in a behavior tree is modularized in individual logic and can be reused depending on the situation and its purpose. It also makes it easy to connect and disconnect specific behaviors at runtime, as each node is executed sequentially in the order of its binding to the tree. So as we saw earlier, behavior trees are comprised of different types of nodes, each node having a specific purpose and behavior. Before we get into the details of each node, however, let's first stop and take a look at the anatomy of a leaf node, a type in MapleStory Worlds known as BT node. The leaf node contains the core of our behavior. Leaf nodes, when connected to an organizational node, such as a sequence or a selector, as we'll get into in just a moment, receive events by default by the AI component that controls the behavior tree. Our first event is the onInit method, which is an event that is executed just before the onBehave event is called. This event is intended as an initialization function and is called just before the onBehave event is called, but not called while the running status, returned from the onBehave event, is returned from the node. The onBehave status is called each frame and holds the core of the node's behavior. OnBehave will return certain statuses that let the AI component know that a node was successful, running, or failed. As mentioned, the onBehave method returns a type of behavior tree status. There are three possible behavior tree statuses: success, failure, and running. Success notifies the parent node that the current node was successful. Failure, conversely, notifies the parent node that the node has failed. Running will cause the AI component to return to the specific node on the next frame until a status of success or failure is returned. Remember that for a node that is called due to the status returning running, it will skip its onInit method call. So here's a sample of BT node, or a leaf node. In this example, the node will keep itself running until a fixed time, in this case 2 seconds, has elapsed. Notice that the running status is returned as long as the timer is running. And if the game ends before the timer has elapsed, the failure status is returned. Because the running status was returned, the onInit method, which initialized the elapsed time to 0, is not called until the running status is changed to a different status. Otherwise, the timer status would perpetually be stuck at 0 due to our onInit call. So we know that leaf nodes return different statuses to their parents, but why does this matter, and what do they do with these statuses? Well, there are certain organizational nodes that manage their children in different ways depending on which type of node it is. These nodes don't inherently contain or execute any behavior, and their sole purpose is to manage and control the execution of their children. So let's take a look at some of these. First up is the sequence node. The sequence node checks the statuses of each of its children and executes them in sequence as long as the statuses remain success. As soon as failure is returned, the sequence node stops executing at its current child node and returns a failure status to its parent. If all children execute successfully, the sequence node returns success to its parent. Here, we see an example of building a tree that contains a sequence node. We've got the root node, which is created as a selector node. More on this in a moment. But to this node, we attach the sequence node. The sequence node is given 3 children in order, action 1, action 2, and action 3. Then we let our AI component know that the root node should be the selector node. So our root node listens for the statuses coming in from our sequence node and manages its connected nodes, if there are more than one, depending on its node type's management behavior. The sequence node listens for each of its children's statuses and returns the final result to the root node. Note that these organizational nodes don't always have to have a leaf node as its children. The root node in this example has a single sequence node rather than a leaf node that executes a certain behavior. The selector node, as we just saw from our previous slide, behaves very similarly to the sequence node, except that the selector node doesn't care that one or more of its children return a failure. As long as at least one node returns a success, the selector node returns success to its parent. This is especially useful when you want to ensure that all children execute regardless of its status, rather than stopping in its tracks as soon as a child returns a failure the way the sequence node did. Let's take a look at another example. This time we've got a selector node as a root and another selector with 3 leaf node children. The selector node will execute each one of its children regardless of its status and will return success if at least one of its children return the success status. Otherwise, the selector node will return false if all children return failure. The random selector only communicates with and executes a single node randomly based on the assigned probabilities. The random selector node draws a random number and selects a node with a probability in the range to which the random number belongs. For example, when the random selector node has 20%, 30%, and 50% probabilities of a child node being selected as shown below, Action 2 node will be executed if the random number is determined to be 40%, and Action 3 will be executed if the random number is determined to be, say, 90%. In this example, the random selector is assigned 3 leaf node children, each with different probabilities. Action 1 with a probability of 20%, Action 2 with 30%, and Action 3 with 50%. So at a random chance, just one of these nodes will be executed and its status will be returned by the random selector to its parent. Remember that the sequence node halted its child node's execution upon failure, and the selector node executed all children regardless of status but considered failures a success as long as at least one of its children were successful. The parallel node behaves very similarly to the selector node in that it executes all of its children regardless of status. However, the final result sent by the parallel node is an all or nothing behavior. This means that either all children are successful or none of them are. So even if one of the child nodes are a failure, the next node will still execute, but the parallel node will return a failure status to its parent even if the next node was a success. The general structure for building trees is hopefully starting to look very familiar by now, enough for you to visualize a tree in your mind by the code. Here, we've got a parallel node and 3 children. As mentioned before, the parallel node will only return a success if all children are a success. However, it will still execute all of its children even if there was a failure. Okay, so here's our first organizational node type that breaks from the format a bit from what we've seen so far. The Decorator node is not a built-in type that is already offered the way that others, such as the selector, sequence, parallel, or other nodes have been so far. Rather, the Decorator is more of a programming design pattern that we're using in the sequence to help you build our tree. Decorators are generally known to be wrappers of existing types and add functionality to the type they're wrapping. Hence, they decorate the target. In this case, our decorator wraps node A and adds conditional logic to our code to decide which node to execute depending on the scenario. The decorator generally holds a single node, but we can step outside the rules of the decorator pattern a bit if desired to add as many nodes as we want and add conditional logic that decides which child to execute next depending on the case. Here's a sample of a tree built with a decorator. First, we'll define our own decorator type that we've created as a BT node type file in our maker. We've created a child property to hold the child node that it wraps. Then we'll create our child node, node A, and assign the decorator's child value to node A. Then in our decorator's node logic, we'll define a conditional for transitioning into that node. Let's take a look at that next. So here we can see our decorator node. We'll initialize our node's properties in the onInit by referencing the parent AI's entities components for the monster and the monster state controller components. In the onBehave, we'll grab our target through a method in our monster's component, and if the target exists, we'll move into our child and execute it. We can imagine that our child has some sort of follow target behavior on its onBehave method to begin following our player. So here's a challenge for you. I'd like to challenge you to pause the video right now and try to work out in your mind the sequence of execution of this tree, assuming that all nodes return a success. How did you do? Did you get that right? Depending on the node, the tree's behavior will of course change as we've gone over today. So we've gone through all the different types of nodes so far, including the special Decorator node to add behavior to our existing nodes. Remember that the running status will cause the tree to return to the node that it's currently running and continue executing the node until the status is returned as a success or as a fail. Awesome, so now that we've got the theory down, let's walk through a practical example together. We're going to implement some AI that patrols around different waypoints, looping through its initial waypoint for infinite patrol, until a player enters into its range. If it does, our AI will begin following our player, and as soon as it leaves the range, it'll return to patrolling. I'd like to challenge you again to pause the video and try to come up with the behavior tree for this AI. As a hint, this tree is relatively simple. It consists of just 5 nodes, including the root. Can you think of what that might be? Chances are, your tree looks different than the way mine does, depending on how you've planned to execute on this behavior. In our tree, we'll have a selector node at the top to ensure that our node doesn't halt when we get a failure from one of its children. Then we'll have a hasTarget decorator to decide whether or not a target is in its range. And if so, we'll proceed to our leaf node, actionFollow. If there's no target, because we've selected a selector node, we'll continue to our patrol action leaf node, and our selector node will resolve overall as a success. Let's now change gears into Maker to work through implementing this together. Okay, so here we are in Maker, and for today's project, we're going to be working in Rectile mode. So please make sure to set up your project in Rectile mode up in the tile setting. And we use the Hennessy's default types to set up a little diamond here that our bunny agent is going to patrol around each corner of our little diamond and protect our diamond from any passerby players. So on our bunny, a couple important components to make sure that you have attached is our trigger component with our collider type set to our circle. We've set the circle radius to around 3. We've also added a collider visualizer, which if we press play here, will allow us to be able to visualize our bunny's collider at runtime. We've also got our AI component that we're going to be communicating to build our tree. And we've also got our character component that we're going to start building out right now. Lastly, we have our kinematic body component, which is critical for functionality and movement in Rectile mode. Okay, with that said, let's open up our character component, and we are going to be building out our build tree method here. So on initialize, we have our build tree method being called, and at the moment, we don't have any functionality. We're going to fill this out with our actual tree so that our AI knows what to do and how to behave. We also have a reference to our AI components, which we need to build our tree. So going back to our behavior tree diagram, we see that we have our selector and we have a decorator, actionFollow, and actionPatrol. So in total, we need to create 4 nodes, not including the root, to have our AI operational. So the actual physical nodes that we need to create is our Deco hasTarget, our actionFollow, and our actionPatrol. So let's hop back into the Maker and see what this looks like. Okay, so as we saw in the diagram, we're going to create our nodes. So let's create a folder to house these nodes. We'll call them AI nodes. And let's right click and create a BT node type for our Deco hasTarget. And we'll create another node for our actionFollow. And finally, one more for our actionPatrol. Okay, so now that we got all 3 of these, let's first build our tree, then we'll go into the individual nodes and build out the behavior. So we know that first we need to have a sequence node up at the top. So first, let's grab our AI component. So we'll go local AI comp equals self.t.ai comp. Just to make it a little easier, we'll do the type handle, and we'll make sure that we know that this is AI component. And we are forcing the type to AI component. Okay, so first thing, we need to create our selector node. So we'll do local selector, and we'll do selector node, and add in our main selector. For the root of our tree, then we're going to add our action follow, and we'll use our AI comp to create a new node. And we're going to name this follow node simple. And we're going to pass in the node type action follow. And we're going to name this node action follow. Let's also define our decorator. So we have our deco has target, and we're going to use AI comp to build that node. So we're going to create node, pass in our type, it's deco has target, and we're going to name this the same thing as target. You can name this whatever you want, but we're just going to use the type as the name. To build this relationship here, we're going to have to set our action follow as a child of deco has target. So remember that our decorator will have a variable child that we assign our action follow to. So we'll open up our decorator, deco has target, and let's create a property, any, and we'll call this child. Let's create a new method and name this set child, and we'll pass in any of the child node. Then we'll set self.child to child node. So now that we have that, we'll go back into our character component, and we'll do deco has target, and we'll do set child, and we'll pass in our action follow. Now in our decorator, we're going to define behavior that will conditionally transition our node into this child node depending on the condition that we set. For now, let's continue building our tree. Notice that we have a squiggly, but we can just ignore that. We have automatic typecasting so that it knows that our type is a deco has target type, which is a child type of our inherited type of our BT node type. So we've got the left side built out. We haven't connected our decorator to our selector yet. Let's first build our action patrol. So we'll do local action patrol, and we'll create our AI comp create node, and we'll pass in the type, which is action patrol. And we'll just name it the same thing, action patrol. Again, you can name it whatever you'd like. Then to our selector, we'll connect both of these. We'll connect the action patrol, and we'll connect our decorator. The decorator already has a relationship to the action follow node contained within the component itself. So we're just going to do attach child of our deco has target, and to our selector again, we'll attach child and attach our action patrol. So now we've got our selector attached to our decorator and our action patrol. And then finally, we're going to set the AI component's root node to the selector so that when the AI component begins executing on this tree, it will start from the selector and begin its decision tree. So we're gonna do AI comp and then set root node and set the root node to our selector. And that's it. We've built our tree. And now we have to go in and fill out our individual leaf nodes for their behavior. So let's go back to our decorator and let's create a reference to our character component so that we can reference some of the behavior here, namely the character in range, so that we can use that to determine whether or not there is a character in range, and then delegate our action to our action follow to begin following the character. So we'll create that reference. We will do component reference to our character component, and we'll name this our character, my character. Okay, and then on the onInit, which is our initialization event, we're going to set the self.myCharacter to the self.parentAI.entity.character component so that we can reference that character. So now we have a reference to our character, and we can access the character in range method. And if you take a look at this method here, we basically just grab all the nearby players, which is assigned based on the trigger enter and trigger leave events. So the trigger enter adds to this table that we have up here, and the trigger leave just removes them from that table. So the character in range loops through all of them, and based on the nearest distance, we'll assign the nearest player and return that back from this method. So we're going to take advantage of that method that already exists in our component. And on the onBehave, let's grab our nearest player. And then if our nearest player does not exist, we're going to return a failure from this node. So our decorator has target is going to return a failure. And then because it's a selector node, remember that as long as there's at least one success, the selector returns a success. So the decorator is going to return a failure if there's no character in range, and then it's going to move on to the action patrol and check for successes there. Okay, so if we do have a character in range, we're going to start behaving on our child. So our child is going to be our follow node, and it's going to begin following as soon as we have a character in range. So that's our decorator. Now let's flesh out the follow node. So the follow node is also relatively simple. We're going to just grab our onBehave, and we're just going to grab our character. So let's do local my character equals self.parent.ai.entity.character component. So because our follow node was not naturally called by the AI component, it was instead called by our decorator, the onInitialization is not automatically sent to this node. So that's the reason why we have to grab our character component, and our onInitialize wouldn't actually be called here unless we called it from our decorator itself. So we're just going to grab our character component here, and then we're going to grab our target. Then from that target, we're going to grab the kinematic body component, and we'll also grab the kinematic body component from our parent entity. And then we'll do a quick validation check to see if that our target exists. If it doesn't exist, then we're going to set our move velocity to 0 and set our behavior tree status to failure and return that. Then if we have a target, we're going to set our move velocity to the normalized direction. Then we're going to set our move velocity to the normalized direction vector multiplied by the delta time and the character's move speed. So our character has a move speed method that is going to return, and at the moment that is just set to 50, but it can be whatever we want based on the value set in the inspector. And that should take care of our follow node. So as soon as our character enters into the range of our character, it's going to begin following our player. Lastly, if our decorator returns a false, it's going to default to the patrol behavior. So to add that action now, we're going to create a reference to our character component again. So we're going to search for the character component, and then we'll name this my character. And let's create an integer value, which is going to be an index of our path. So we'll name this path index, and let's default that value to 1. So this is going to keep track of which index of the path we are currently on. So in the onInit, we're going to initialize our character reference. So we'll grab that character, and in the onBehave, let's first grab the waypoints. So in our scene, we have 4 waypoints, each at their respective corners. So we have a waypoint here, 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 and here. And all of these are just empty entities with a transfer component attached. We have a parent waypoint that we reference, and then in our get waypoints, we simply just grab the children of the waypoints, and we're going to change that to a table and return that. So that's how we're getting all of our waypoints in sequence. And then let's grab a couple things from our component. So we're going to grab our kinematic body, which we're going to use to set the velocity of our character. And let's grab position from our character's transfer component and set that to vector 2. Then we'll set our target waypoint to the current path index. So it's going to start at 1 and grab that waypoint's transform component. And we'll set the target position to the target waypoint and set that as a vector 2. We'll do a quick validation to make sure that our target waypoint exists. Then we're going to check the distance, and we're going to create a directional distance vector. and we'll get the magnitude of that so that that will give us our distance, and check if the distance is less than 0.2. If that's the case, then we've reached our waypoint and we're going to increment our path index. If our path index is ever greater than the list of waypoints, then we're going to set the path to 1. Finally, we'll set the move velocity to our normalized direction vector between our target and our current position, multiply that by our delta frame value, and then get the character's movement speed and multiply that to the final value. And that will give us our move velocity. And finally, we'll return a success. And that's everything we need for our simple AI behavior. Let's go back to the scene and test everything that we've got so far. So we forgot to assign our parent value. So we'll go into our monster and we'll search for the character component and we'll assign our waypoints parent. And let's press play one more time. Okay, so because we don't have a character in range yet, it's going to begin patrolling our diamond. So it's going to continue patrolling, doing its job, until which case our player comes into range of our bunny. As soon as it does, as soon as we outrun our bunny, which doesn't seem like we can, let's slow the bunny down a little bit so that we can check that. Let's set our movement speed from 50, let's set it down to maybe 20. So our bunny begins to patrol this area, and then we will enter into the range, and then it'll stop its patrol and begin following us. When we leave, it's going to return back to patrolling. And when it reaches its waypoint, it will move on to the next waypoint. Okay, so just to verify that our bunny is actually moving across all waypoints, we're going to increase the speed to 100, make it super fast. It's going to zoom across our diamond. So it's running across our diamond, moves to each waypoint. And when it reaches the very first one, it loops back to the beginning and continues the cycle following the diamond. And that's everything for today. AI behavior trees can be incredibly powerful when it comes to building out these trees and defining behavior for your AI models. Hopefully you've learned a lot today, and I can't wait to see how you implement AI in your own games.